these synthesis examples involve reactions in chapters 17 and 18. So it's substitution reactions to the benzene ring and modifications of those. And the questions here range a fair amount from putting groups to make disubstituted benzenes, trisubstituted benzenes, and these first 6 reactions all involve just electrophilic aromatic substitution and modification of the groups. When we get down to this one, we'll be using some reactions from the end of chapter 18. And then this last set of 3, is going to use the diazonium salts that are in chapter 22, but that we include with the chapter 18 material because it's such a useful way to make substituted benzenes. So when we look at these, a couple things we're going to want to do is, first of all, look at the orientation of the groups on the product. So for example, this one up here, the 2 groups are meta to each other. And then you're going to look at what gets added. Is it something that you can add in one step? So for example, here you would add a bromine and a chlorine. Both of those can be added in one step. If it takes more than one step, is the directing effects going to be the same for the initial thing you add or for what you turn it into? And are there any issues? So for example, you can't do a Friedel-Crafts if you already have a meta-director on the ring. And one thing you always want to do is compare the orientation in the product to the directing effects of any groups that you're attaching, and again, their precursors. All right. So for this first one, we have 2 groups that are meta to each other. This one is an orthopara director, this one is a meta director, but you can't just stick the NO2 on and then add the alkyl group because, again, Friedel-Crafts alkylations aren't going to work with that nitro group on there. The other issue with this is that if you try to install a primary alkyl group, it's going to rearrange, so you're not going to get that. So what we need to do is acylate and then reduce that. And that will actually solve our other issue as well, because when we have an acyl group here, that will direct the nitro group so that it actually goes meta. So our strategy here is going to be to acylate, nitrate, and then reduce the carbonyl. And more on how we're going to do that in a moment. So we acylate with the acid chloride and aluminum chloride catalyst. Then when we nitrate the resulting compound, the nitro group goes meta. And now what we need to do is reduce this carbonyl to a methylene without affecting the nitro group. And it turns out you can do this with a Wolff-Kishner reaction. It involves some chemistry that we talk about in the aldehyde and ketone chapter. But you take the carbonyl compound and you react it with hydrazine in acid and then heat it up in base. And the advantage of that here is that this will reduce the carbonyl without reducing the nitro group. It turns out that the Clemmensen reaction will reduce both, which is handy if that's what you want. So we'll go ahead and use this Wolff-Kishner. I'm not going to make you do any synthesis questions where you would have to use that for now, but it's something that you could use. And if you're curious, it's covered on page 867 of the Klein book. So the second one, we have, again, 2 compounds that are meta. Both are orthopara directors. The halogen we can put on in one step. It has no issues. The halogens are really pretty robust once they're on there. The NH2 group is not only an orthopara director, but it's got some issues. If you just tried to halogenate the aniline, basically the chlorine would go everywhere except the meta position. So what we're going to do, since the NH2 group is produced by reducing the nitro group, we're going to nitrate. That's a meta director. When we chlorinate, it will go meta, and then we need to reduce the NO2 to an amine. So coming over here, we're going to first nitrate to make nitrobenzene, then we chlorinate, that goes meta, and then we can use this process to reduce the NO2 to an NH2. And the function of the NaOH is that when you produce the aniline in acid, it's going to be protonated. So the function of the sodium hydroxide is just to reform the base or free the base. So now here we have a compound where the two groups need to be ortho to each other. And we have one ortho-para director, one meta director. And again, this is not only a meta director, but it would make it impossible to add the alkyl group anyway. If these two groups were para, our task would be relatively easy. We could just alkylate and then nitrate and we'd be done. The problem is that we're going to get more para than we are ortho, and we want the ortho. And so this is a case where we're going to use sulfonation as a blocking group. So concentrated sulfuric acid installs the group, more dilute sulfuric acid removes the group. So our strategy here is going to be alkylate, which will work fine. There's no rearrangement here. Block the para position, nitrate here, and then unblock. So we alkylate with isopropyl chloride, and then we use fuming sulfuric acid, which is highly concentrated sulfuric acid. It's called fuming because SO3 comes out of the solution, and when it reaches the water vapor in the atmosphere, you actually see fumes. So that installs the SO3H group. Now we can go ahead and nitrate, and when we nitrate, this group is going to direct it meta to it. This group is going to direct the incoming electrophile here, so both groups are sending it to the same place. So the nitro group goes here, and then finally we can use dilute sulfuric acid to remove the protecting group and get our ortho product. Number 4. So now we have two ortho-para directors that are meta to each other. But we're saved here again by the fact that the only way to get this alkyl group on here is by acylating and then reducing. And the acylated group, the acyl group, is going to be a meta director. And we want to use this precise issue. We want to acylate, then chlorinate, and then reduce, because if we switch this order and reduce before we chlorinate, then the chlorine is going to end up para and not meta to our alkyl group. All right, I just realized that this is wrong because I have an extra carbon in there, so I'm going to fix that, hopefully semi-quickly. So now we have 1, 2, 3 carbons, 1, 2, 3 carbons, and we're good. So we add our acyl group. It is kind of easy to lose track of these carbonyl carbons, which is exactly what I did. So we acylate, then we chlorinate. When we chlorinate, the chlorine's going to go meta to our acyl group. And then we can use the zinc-mercury amalgam with HCl and heat, and that will reduce the carbonyl to a methylene, and we're done. We could have used the new reaction that I introduced in the first one here, that Wolff-Kishner as well, and that would have also worked. All right, now we move from the realm of disubstituted benzenes to trisubstituted benzenes. And as we move into this area, sometimes it's helpful to think about working backwards to do this so-called retrosynthetic analysis. If nothing else, think about what group needs to go on last. So if you think about what group needs to go on last, then it becomes a disubstituted benzene problem. So here it makes the most sense to chlorinate last, because if we have this acyl group and this alkyl group, both of them are going to direct this chlorine solely to the place that we want it. If you look at some of the other possibilities, it's just not going to work as well. If this is on here, we can't add that, so that's out of the question. And if these two are both here, yeah, you're going to get mostly this, but you're going to get significant amounts probably where you add it there. The one saving grace here is that this is an example of something that's not going to rearrange, so we can just alkylate. So what we want to do here, alkylate, then acylate, then chlorinate. So it's a relatively simple three-step process because all three of these groups can be put on directly without any issues. So here we go. We alkylate with the isopropyl chloride to make isopropyl benzene, also known as cumene. And then we do our acylation, which is going to go mostly para. You might get a tiny bit of ortho. It turns out it's pretty easy to separate para compounds from ortho compounds. The para is so symmetrical that they'll tend to have significantly higher boiling points, or sometimes even this will be a solid and these will be liquids. And then we're going to go ahead and chlorinate this, and both of the existing groups are going to direct the chlorine to the correct place. And as I noted here, this is not so bad for a trisubstituted benzene synthesis because none of the groups needed modification. However, we'll do the next one. So in number 6, now we have a scenario where two of the groups, the NH2 group and the alkyl group, each have to be put on one way and then modified. So in the case of the NH2 group, we have to do it via a nitration and a reduction, which changes the directing effects. And again, here we need to acylate and then reduce. And again, those two things have different directing effects, the acyl being a meta-director, the alkyl being an orthopara-director. So again, we're going to put the chlorine on here while this is still a nitro group, because if this is a nitro group and this is an alkyl group, again, the only logical place to put the chlorine is there. Unfortunately, this means we have to reduce in 2 steps. So wrote out an example of a retrosynthetic analysis. It's kind of small, but we can deal with it. So there's our target compound. So these funny open arrows are retrosynthetic arrows, and it just shows that we're working backwards. So we would get this by reducing the nitro group. Then we would get this by chlorinating this compound. And then between the nitro group and the alkyl group needs to be on there and is an alkyl group before we nitrate, so it goes para. And then the alkyl group comes from the acyl group, which in turn comes from benzene. So again, that's another way of tackling these by logic or words or retrosynthetic analysis. So moving forward, this is what our synthesis is going to look like. So the first thing we're going to do is acylate again. And now we have to reduce this acyl group, and we could again use whatever method, and we're even going to learn a third method to do this in the next chapter. We reduce it, now we have our unrearranged alkyl group. When we nitrate this, it's going to go predominantly para. Now we can add our chlorine, and again, there's only one logical place for the chlorine to go, or two logical places that are the same. So these two positions are the same, and that gives us this compound, and now we're almost there. All we need to do is reduce the nitro group to the aniline group. All right, now we're going to be looking at a reaction that we learned towards the end of the chapter. If you look at this, this is a nucleophile, and we're not going to add a nucleophile by electrophilic aromatic substitution, so we need to use some sort of nucleophilic aromatic substitution. And so we've got SNAR, or we can use a benzyne. Generally, the benzynes really don't have great synthetic applications, so it's usually going to be the actual nucleophilic aromatic substitution mechanism, the mechanism that involves addition and elimination. And in order for that to work, we would need a leaving group at this position, so some sort of a halogen, and we need an electron withdrawing group, para, and or ortho to it. Well, we've got the nitro. So in this particular case, if we put the chlorine on first and then nitrate, the nitro group will go into the para position. And again, this chlorine goes on last, because if we have a nitro group here and this orthopara director here, the chlorine will go here. So the chlorine goes on last. Prior to that, we do the substitution to replace the halogen with this nucleophile, and then from there. So we're going to chlorinate because we need a leaving group, nitrate, do the SNAR with ethoxide, which is a perfectly legitimate thing to do, and then chlorinate. So working forward, we chlorinate, we nitrate, and then what we're going to do here is add sodium ethoxide and heat it up. We could also make a phenol, so you could add sodium hydroxide, and then that would give you in base that anion that would then do a nucleophilic attack on ethyl bromide. Either thing is fine. At any rate, once we have this nitrated ether, we're going to chlorinate it, and the chlorine will go there. By the way, I'm not snoring. My cat is. For some reason, every time I try to do this, he decides it's time to play or sleep. Okay, now for the last set of reactions, 8, 9, and 10. These are all going to involve diazonium salts. And we have a pretty good clue with this first one that we're going to need a diazonium salt, because the only way we have of installing iodine, unless you look at some of the tricks that are just in the problems and not in the body of the text, the only way we have of putting this iodine on is with a diazonium salt. So we're going to have to nitrate, reduce, and then diazotize, and then add the nucleophile. Notice here we've got two orthopara directors that are meta to each other. But we're going to have to acylate and then reduce this to avoid rearrangement anyway. So we'll have a meta director here, and then the iodine also goes on ultimately via a meta director because of the nitrate. But we're going to need to acylate first and then nitrate because, again, the acylation won't work with the nitro group. So a teeny tiny retrosynthetic analysis. So there's our final product. We know that the iodine is put on via the diazonium salt. Ultimately, the diazonium salt comes from the nitro, and the alkyl group comes from this acyl group, and that in turn we can nitrate this species to get that. Once I started to write this out forward, I realized that there actually was a simpler way when I was in the middle of it, so I went with that. Okay, so once again, the first thing we do is we acylate, and then we nitrate. And now the thing I realized as I was writing this out is that you can use a Clemmensen to reduce both a carbonyl and a nitro group at the same time. And so what I did is I used my Clemmensen, and I wrote excess everything because I want to reduce both groups. And that's going to reduce the carbonyl to a methylene and reduce the nitro group to an amine. But I thought since it's in hydrochloric acid, this would be protonated, so we would need to add some sodium hydroxide to liberate the aniline as NH2. And then you can take the NH2, diazotize it with sodium nitrite and aqueous HCl at low temperatures. You're never going to isolate those diazonium salts, so you don't have to show the diazonium salt as a synthesis intermediate, but you may if you want. And then we're going to add cuprous iodide, and the iodide replaces the N2 group, and nitrogen is released. So nitrogen gas is evolved when you do this. And the copper 1 or cuprous salt is actually thought to play a role in the reaction, but it is one of those not well understood mechanisms. Number 9. So here again, we have a group that we have two ways of putting on, one via a diazonium salt, one being via a benzyne, not a benzyne, probably nucleophilic aromatic substitution. But the nucleophilic aromatic substitution isn't going to work because we don't have that nitro group here. We have an alkyl group. So we're pretty much stuck using a diazonium salt, although it turns out that that's pretty easy to do. So in this particular case, what we want to do, in theory, you could alkylate with this OH here, or you could diazotize, you could nitrate the tert-butylbenzene and then go on and make the diazonium salt. But this is kind of a more robust side chain, so I'm going to go ahead and put that on first. So we're going to alkylate, nitrate, and then convert the nitro group in 2 steps to a diazonium salt. And then literally all you have to do is warm the reaction up, because the water that's the solvent in the aqueous solution is going to replace the N2 group with an OH group. And that's something that can actually happen to a diazonium salt when you don't want to have it happen. So the full synthesis looks like this. We alkylate, no problem with rearrangement here. We nitrate, no problem with getting ortho as opposed to para product. Then we reduce the nitro group to an NH2, diazotize it, and then just as I said, simply let it warm to room temperature, and that will make a phenol. And finally, we have this meta-dihalogenated compound, and here we need to install 2 ortho-para directors that are meta to each other. And one way to do this is via a diazonium salt, because the diazonium salt nitrogen ultimately comes from a meta-directing nitro group. This isn't as obvious otherwise that you need to use a diazonium salt, because both of these halogens can be added other ways. But in order to get them in this position, we need to use a diazonium salt. So what we're going to do is nitrate, put the nitro group on, halogenate so that the halogen goes meta relative to the nitro group, reduce and diazotize the nitro group, and then add the other halogen. It really doesn't matter which halogen we add first, because both can be added directly to the ring, and both can be obtained via a diazonium salt. So we just kind of have to pick one. All right, so the first thing we're going to do is nitrate our benzene ring to make nitrobenzene. And I chose to brominate first. I don't know why. I just chose to brominate first. Maybe bromine is slightly less nasty than chlorine, who knows. And you can just do that with bromine and iron, and then that generates the ferric bromide in situ. So the bromine is going to go meta to the nitro group. And now we can reduce the nitro group to NH2, convert the NH2 into a diazonium salt, and replace the diazonium salt with chlorine via cuprous chloride. And now we've managed to get our two orthopara directors meta to each other.